Everyone is here, right?
Yeah, yes.
So, so should I? Okay, yeah. Hi.
Co-host.
Yeah. So I'll record this.
Yeah, you can start recording. I've also started the co-host.
Yeah. Okay, I think both the recording and the live stream is happening right now, right?
You can start.
Yeah. Okay. So yeah, I'll start.
Sorry about that. So I'm extremely sorry. Yes.
So yeah. So can everyone see the screen?
Yes.
Yes.
Okay. Okay. So just 1 second. Let me adjust this. Sometimes. Just a minute. Yeah. Okay. So right. So we were looking at BDDs last time, and we had just finished talking a little bit about what the idea behind these COBDTs were, right? So does everyone remember the point at which we stopped there? Okay. So what I planned last time was that after that I'd like just go through just constructing this BDD with you guys with this particular variable ordering. So does everyone feel confident with this BDD, or do you like want to do this example right now, this particular example? Otherwise I'll move on. So yeah, do you want me to do this? Yes or no?
I'm okay with you moving on.
Running
Yeah.
short on time.
Yeah.
Yeah, actually I saw this example.
Yeah. Okay.
You
Sure.
post it, right? So it's okay.
Right. Okay. Sure. All right. So okay. Yeah. So I have the definition of BDDs here, and this is basically trying to make a formal definition out of this. So one of the things that I like want to basically emphasize on, which I think I talked about, is firstly a canonical form. So every function has one unique BDD. Also, what we maintain in any BDD implementation is that even when you're dealing with multiple functions in your memory, you will have exactly one node for each function. So even though like firstly for any function there should be only one BDD, and you'll only carry around one BDD even if you have like multiple appearances of the same function, one BDD node for each function, right? So if you find that this BDD node 4 appears in some other function as well, like say for example you're working with memory and you end up introducing this BDD, the function represented by this BDD node 4 again, a good BDD implementation, and that includes this UDD BDD implementation that we'll talk about today, what that will have is that instead of constructing a separate BDD, it will actually just give you a pointer to this node. So what is always maintained is that you have one node and one node exactly for each function that you want to represent, right? So this is something that I wanted to emphasize once more, right? So now we come to some useful observations regarding BDDs. Right, so I'm sorry about that. Yeah, so variables always occur in any specific ordering. So you basically fix the ordering of the variable, and then that gives you a particular BD. Now every path from root to the terminal 1, right? So now from henceforth, we will, when we say BDD, we will usually mean just normal BDDs, not COBDDs. But everything I say will sort of have corresponding statements in COBDDs as well. And you can sort of think of that. And if you're confused that, if you think that something I'm saying will not work for COBDDs, interrupt me and ask. Right. So every path from the root node to the terminal 1 is a set assignment, right? And for COBDDs, the corresponding thing here would be that if your path has like even many complemented arcs, then it's a SAT assignment. And if it is an odd many complemented arc, then it is not a SAT assignment, right? It's an unsat assignment. So both for BDDs and COBDDs, you can sort of go over the paths and that will enumerate your assignments for you. Now every node includes a Boolean function, and yeah, so there is exactly one such node for each function. This is what I was talking about. And this is interesting. So notice that since there is only one function, exactly one unique BDD per function, and if you can sort of think about the a valid formula, let's say, a valid formula is essentially just a constant function, right? So valid formula essentially looks something like f x y z something something equals 1, right? So that means that all valid formulas should just have a single BDD, because as a function they're all the same, and that BDD should just be the constant node 1, correct? For COBDDs, it will be something like a solid edge to a constant node 1, right? Similarly, all unsat formulas are identical to the BDD 0. So if your formula is unsat, that means it's a constant function again, and it's 0 this time. So with 0, again, it should just be the constant node 0, right? And for COBDDs, it will look like you have a root node, and then you have a dotted and complemented arc to the 1, right? So since, all your valid formulas are 1 and all your unsat formulas is 0.
Actually, Diganta.
Yeah.
So this, if for 0 complemented thing, the 1 will also be one copy. Therefore,
Yeah.
it will actually go back. I mean, just a minor point. That's also
Right. So the point that you mean is basically it'll basically look something like this, right? So you'll have 2 root nodes and sharing the same one node, right?
Correct. That's what I mean.
Yeah. So this will basically be your. So if I have an f and f tilde x y z, let's say, equal to 1, then this will basically be your. In this case, this is f tilde and this is f, right? So again, like, you don't want to share even just the one node between different functions. So if in your program you have both a SAT and an unsat node, they'll all valid formulas will basically point to this node here, and all unsat formulas will point to this node here, right? So now that we know that for BDDs and for COBDDs, your situation is that every valid formula is just identical to this node. It's going to be pointed to this node, and every unsat formula is going to point to this node. Checking whether a formula is SAT is actually constant time, right? You just check whether it is BDD 0 or not. Similarly, checking whether it's valid is you just check whether it's BDD 1 or not, right? Now this is very weird because SAT is supposed to be hard, right? So what is the catch? Like, what is the what prevents this sort of thing to be happening? Like, it can't be that we can just do a SAT check in constant time, right? So any guess?
Maybe constructing the tree will be.
Yes, exactly. So constructing the BDD is going to be hard, and in fact, it is often exponential. So that is what we are going to see. But let's think about it more deeply. What does constructing the BDD or let's say, what does the BDD size depend on, right? So one question is how hard is it to construct the BDD, but there's also this related question, and we'll see why these are related, is that what is the size of the BDD, right? So essentially, whether or not you are able to do this in polynomial time or not, which you shouldn't be able to, which we'll see, but how often you're able to do this in polynomial time or not depends on your size of the BDD and how easy it is to construct. So let's look at what the size of the BDD depends on. And that is basically depends on what order you choose for your variables, right? So let's again consider this A equivalent to C and B, like A equivalent to B and C equivalent to D BDD, right? And as we saw before, this is the BDD for it. So here you have the BDD, and if we just not draw some of the edges and simplify this, it will basically look like this, right? And this is fairly compact. I mean, we are sharing here this C node as we saw last time, and there would have been multiple occurrences of these D nodes as well, which would have been shared. This is the same BDD as we were talking about before, just the variable names are different, right? So yeah, so this is fairly compact. But what happens if you change the variable ordering? If you change the variable ordering and say that instead of ordering it as A, B, C, D, we instead go for ACBD, then you'll see that the BDD basically becomes this really complicated structure, right? I mean, it's basically much bigger than this other BDD, and it's far less compact, right? And you can sort of work this out on your own and see that it'll be the case, right? Because say if A is true or false, based on A is true or false, the next decision that you need to take is whether C is true or false or not, right? So if A is true or if A is false, and then if C is true or if C is false, it doesn't let you immediately go to 0 or block some particular decision or immediately say that, okay, we know that the output will be 0, which we could in the previous one, right? If we had decided based on A and then B, the moment we know that, okay, A is true and then B is false, then we know that we can directly go to 0. So we don't need any more nodes here, essentially. So here we can't do that because of the particular variable ordering that we have chosen, right? So if we assume that A is true in our case, if we assume that A is true and that C is true, that really doesn't let us go to anywhere other than the B node. And similarly, if we choose C to be false, we again have to go to a B node and make some decision, right? So that's why the size of the BDD ends up growing much bigger in this case. Now, another much more drastic example is this, right? A1 and B1 plus A2 and B2 plus A3 and B3. So if you go via A1, A2, B1, B2, A1, B1, A2, B2, A3, B3, if you use this variable ordering, you get a nice and very compact BDD. But if you use A1, A2, A3, B1, B2, B3, you get this horrible BDD, right? So this is another very drastic example of how much the variable ordering matters. So in general, how would you want to choose your variable ordering, right? So the idea is that whenever you fix or whenever you choose a certain, like some variables, say you've chosen that you're going to make the first decision on A1, and say that you've also chosen, or you're deciding which one is going to be the next variable that you're going to decide on. You would want to choose a variable such that if you know your value of A1 and the value of the next variable, then you can block a lot of other decisions, right? So you can basically make a quick decision just based on that. So essentially, you would want to choose a variable such that your partial assignments are very simple. So if you choose a variable ordering where your partial assignments are always going to be very simple, then you'll get compact BDDs. If you don't, then you'll get huge BDDs. Sometimes it's easy to just look at the formula and think about what is going to be a good variable ordering. But often this is actually this is in fact an NP complete problem, choosing a good variable ordering for a BDD. And in general, there is no good way of doing it. But so this is one of the pitfalls and catches that you have when you're using a BDD based system. So yeah, so order determines the initial partial assignment of the variables. And the more variables the partial assignment enumerates, the more compact the BDD is going to be, right? So yeah, now we come to this question: how do you construct a BDD? So we have seen this fact, right? That that there are basically two catches when you're thinking of doing SAT checks with a BDD, right? One is that the BDD itself can be very large, depending upon your variable ordering and such things. But the other catch that could potentially happen is that how do you even if your BDD is compact, how do you construct it, right? How do you come up with this compact BDD in the first place, right? So one of the ways would be to construct a bottom-up BDD every time. So I'll say what I mean by every time over here. This is basically essentially what we had been doing in the previous one, which is that you go up, you take your formula, you construct the entire decision tree for it, and then you sort of go bottom up and keep merging your nodes as you go bottom up, right? In this order here. And we can do that, but this is not very efficient. And this is because of a few reasons. One is that if you're already constructing this huge tree, this is only slightly worse than carrying around a truth table for your function, right? You're having to sort of think about all the assignments that you're make, like in your complete decision tree, which has not been merged at all. Each path to each leaf node is essentially one whole assignment. So you're sort of carrying around something like a truth table here, and it's as big as a truth table out of comparable size. So this can't be the most efficient way to do it. Like otherwise, it makes no sense to use BDDs, right? Also, oftentimes when you're constructing these formulas, you don't really, you don't want to go through taking the formula, constructing a tree and then working with it, right? You usually have some non-canonical structure for your formula that you want to construct things out of, right? For example, if we look at our given, the form in which this particular formula was given, this is not any, like, not directly, at least it's in any canonical form, right? It's not given in CNF or DNF or anything like that. It's usually given as some arbitrary form, and we would want to sort of figure out a way to construct this formula directly from this arbitrary form without having it to convert to some tree in the first place, right? And maybe that will also allow us
by arbitrary, what you presumably mean is it has all kinds of Boolean connectors.
exactly, yeah, and in known particular order as well. Like, it's not like you have ands and then ors, or ors and then ands, and it might not even be an NNF, right? Even, you could even be given a formula in this form and asked to make a BDD out of it, right? x1 equivalent to y1 whole knotted and then and x2 equivalent to y2. This is not in any canonical form. So we would want to work with these formulas. And another thing that we would like to do is essentially, if possible, this entire idea of BDD is to share multiple variables and so on, right? Multiple formulas with the same node and so on, right? So we would like to make use of that as well while we are constructing this formula. And maybe, there will be multiple copies of the same subformula arising in the form that you're given. And hopefully, not just this final BDD has the sharing, but even while you're constructing, you can make use of that. So how do you do this? Like, how do you construct it in a smart way that, uses the idea of the BDDs, right? So what we want to do is, we would want to basically, instead of going bottom up, we would want to follow the structure of the formula that you're given and keep merging the two BDDs that you have to get the desired results while preserving the BDD conditions. So essentially, you would want to treat your BDDs as some objects which you can and, or, and not. Because if you can do that, then you can, just follow the structure of your formula to get a BDD. So for instance, if your formula is of this form, right, like we had previously, x1 equivalent to x2 not, and say y1 equivalent to y2, right? So there your outermost structure is and. So you can maybe hopefully do something recursively. So if you had some 3 methods or 3 or 4 methods which could, say, take your 2 BDDs, b1, b2, and an operator, and if you could, combine them somehow, merge these b1 and b2 based on the operator to get a BDD b out. If you had methods doing this, what you could do is basically use this and recurse based on the structure of this formula, right? So you have a top level and, so you do BDD of this one and BDD of this one, and then over here, you do a not of BDD of the inner one, and then inside you maybe have something that maybe your operator can be this. So you do equivalent of the equality combination merging of the BDDs of x1 and x2, and then finally when you get to variable level, you can just create that BDD, right? So this is the smarter way to sort of construct a BDD, and this is smarter because of 2 reasons. One is that, of course, while you're constructing this BDD, the sort of the intermediate BDDs that you get, they are also BDDs, right? So the intermediate structures that you are sort of generating here are BDDs, which means that they hopefully will themselves be compact, and you'll be able to work with compact intermediate structures in this, as opposed to having some exponentially large intermediate structure like a tree, right? And the second benefit is that these intermediate structures or BDDs in a good BDD implementation, they'll also be shared, right? So if you had a formula like x1 dot x2 plus, say, x1 dot plus x2 bar, right? And if your BDD implementation, say, uses COBDDs, then what will happen is that you can see that this is basically just a knot of this, right? So once you construct the intermediate BDD for this, you'll basically just be able to construct the intermediate BDD from this, and that will share the same nodes, right? Because you'll have some BDD for some root for the x1 plus x2 bar, and then just not of that will be, so this one of these things will be dotted and arced edge. So just the knot of that will be your x1.x2 bar, right? So here, even when you're working with your intermediate structures, you have some sharing and you're saving some memory. And because you're saving some memory, you'll have to work on lesser structures. So you're saving some computation as well, potentially. So with a good BDD implementation, will basically ensure that intermediate structures are also shared. So this is basically the idea that you want to follow when you're constructing two BDDs, right? You want to go because basically on the syntax of the arbitrary formula that you're given, and you want to keep merging the BDDs that you get. Like, so you want to generate the BDD of the left expression recursively, right expression recursively, and then merge them. So now the question is,
Excuse me.
yeah.
That's good.
Yeah.
So the second point you said,
Yeah.
like if you do it recursively, the sharing will not happen, right?
No,
Because
it will happen. Like a good implementation will actually make sure that it happens. So let's say that you have done this one first, right? So it'll maybe look something like this. So maybe you have some tree here, and then whenever you sort of do it recursively, whenever you get x1, maybe x1 is a part of this tree, so that will point to here. Whenever you get x2, maybe that is a part of this tree and that will point to here. And then when you add them, then you'll get something that basically looks like, so you'll basically end up, this and will end up getting represented at exactly this expression and that knotted. And then when you finally knot it, you just go to the unknotted version, right? Okay, so let me just work through this and you'll see how that works. Would that be helpful?
okay.
Yeah. So let's say that even a simpler example, let's say, right? So say you have just x. So your COBDD structure would look like this. You have this is your COBDD structure for just x, right? And say you have recursively just constructed this x structure, and now say your expression looks like this, right? So you've recursively done the right one first, and now you're doing the left one. So then what happens is that you see that, okay, you want x, so you already have that. So you want to do knot of something, knot of b, and b will point to this. And then when you want to take knot of this, so you would basically just your knot of, like, your b basically is going to look like something like this. And then when you want to take knot of this, you just create another small node here and put a arc here, right? So this will basically become your x bar. So you don't have to redo this entire BDD computation at all. So that is the idea, and good BDD implementations can actually do this fairly well. And
yeah, that's true. But then, Diganta, but you have not actually done the plus yet. Okay, so that's the catch, no? So
yeah, that is the bunch, right? So
yeah.
So yeah. So once you do the plus, then
Yeah,
what
you
will happen is that
still have to show
a lot
how
of
to do the
reductions
plus.
will happen, and right. Yeah. So I'll go down and show that, right? So yeah. So the idea is that if we can actually get these merge functions of this kind, right, and then we can recursively go down the like recurse on the syntax of your arbitrary formula and generate your BDD that way, and that is very good. So we want to somehow figure out how to do this merging, right? So how to given two BDDs and an operator, how do we merge those two BDDs and get an output BDD? So that is what we are going to look at next.
I have a
Right?
question on that slide.
Yeah.
So the example you have shown x1 x2 bar plus x1 bar plus x2 bar.
Yeah.
When we are trying to build a BDD,
yeah,
our system might not know that the first formula is a negation of second one. Right? What it does is it constructs the whole BDD and then checks for isomorphism, right? It constructs the case for x1 x2 bar and then x1 bar plus x2, and then checks whether they are isomorphic, okay? And finds out if they are negated, and then just merges the two branches, right?
No. So that's what I'm saying. It will not have to basically construct a separate node at all. So good BDD implementations are actually smart enough so that when you're seeing that when it
Okay.
sees that this, you're asking for a not of, yeah. So
Okay.
when it's asking for a not of X,
So they can
then
identify.
No, 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 no. I think I would answer it this way. Okay, see, if you were using, if you're using normal standard BDD representation, then of course you'll be constructing not F. But if you're using COBDD like CUDDD package uses, you'll never do that. What you do is every time you construct a function, a Boolean function, the not of it is also automatically constructed. Okay, or it is there. Okay.
Yeah, but my question is that there are two sub-formulas here. So given these two formulas, we have to tell that one is the complement of another, right?
No, 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 you don't need to, because if indeed, just like plus operation, if you were to be wanting some function and you want to apply a not of that, when you're doing the not operation, you know that it's already there. So you just construct this, maybe it's the root, no, I mean, you will know that it is there already, okay? And therefore you will appropriately do it, okay? I mean, that you do when you come across, when you're building the actual Boolean, you're given a Boolean formula, okay? That has a not function. I mean, that has a not operator. So as long as you know that if it's complemented arc BDD, the negation of it is already embedded in there, except that you have to take one, depending upon what function you have constructed. If you, that function is already there, then you know that not of, when you do not of F, it's already in there. Does that answer your question?
I'm still not kind of convinced because.
Okay, I think what you should do, Diganta, show, I mean, for now, okay, ignore, I mean, let's forget the complemented arc BDD, how it is, how this merge operation is done there. Okay, it's because we'll get to that, because that's a little bit more complicated as to how you apply these operations on complemented arc BDD. So I guess that was that was Paramalai.
Okay.
Yeah. So we will get to that question as to how you would do it for complemented arc.
Okay.
Let him first show how this merging or application of operations happen in such a way that the variable ordering is preserved. Okay. On standard things, and we'll actually do as an exercise, maybe. Okay.
That is actually.
So that would be a good idea, because there, it is not easy to see how exactly it is done. It's not so obvious. Yeah, that's what I would suggest. Yeah, go ahead.
So I'll show some examples of working with
Diganta, I have to leave. So you go ahead now. Yeah. Okay.
Yeah.
Thank you.
Yeah, sure. So so let's sort of look at how we would construct this example, in fact. And let's say that, okay, I'm gonna mark this with bars because it's slightly easier to read maybe. But yeah, so let's say that we're working with BDDs, not COBDDs. And maybe I'll be able to show like some of the shading as well in this example. So let's go through these together, right? So let's say that we'll recurse and we'll look at the leftmost branches first. So let's do these examples, and then I'll give you sort of what the algorithm would be to merge two things, right? So in the first one, when you go to the leftmost thing, we see that it's just a variable. So firstly, we create a BDD for just the variable, and that looks like this: x dotted to 0, and then a solid to 1, right? So right now your BDD or your program contains just this as a BDD, right? And now you have a plus. So you want to plus this. So you basically want to plus of two BDDs. So essentially your first recursive call was, say, B1, B2 plus, and then you're dealing with B1. So this is your B1, right? Now you want to construct your B2. So B2 is given by, so this is your B out or B, let's say. So B2 is given by not of like X, right? So you basically want to have another B3 and then a not, right? and B3 is again just X, right? So whenever you, as soon as you say that B3 is just X, then since it's just a variable, your BDD package will immediately set B3 to also point to this node. So it's not going to construct a separate node and a separate structure like this. This is never going to happen, right? This is going to, B3 is always going to point to the same X node, correct? So now you have B3 as this, and you want to set B2 to not of this, right? So how would you not a particular BDD node? So the way you would not a particular BDD node is again going to be something recursive. The algorithm could be something like this, right? You want to not a BDD node means what? Like your BDD node basically says that you have some variable V. If V is true, then you have some BDD, else you have some other BDD, right? So when you want to not a BDD node, what you basically want to, so if you want to take a not of this entire thing, that is equivalent to taking a not of your individual components here, right? So this is equivalent to saying then not of whatever was here, else not of whatever was here, correct? So is this okay? So when you're doing the B3 comma not sort of operation, or not on B3 comma operation, then what you would want to do is basically, this will basically devolve into first do a not on each of the children of the node pointed to B3, and then return the new node, right? So this will basically be return a node which contains as children. So so basically you can define your B3 or any B which is say or not as this, right? So there are two cases. One is if B is basically, you have two children, node L and R. L, or let's say positive and negative. Positive represents the one for where your very decision is true, and negative is the one where your decision is false, right? So if your B is basically a node with two children P and N, and you want to do a not, then this will basically should go to a node which has not P and not N as children. Otherwise, if it is 0, then and you're doing a not, it should go to 1. And if it is 1 and you're doing a not, it should go to 0. Correct? So in this case, B3 is of this form. So this is the case for a recursive function that will basically be triggered. And what will happen is that you'll basically end up creating a new node where you take the not of each of the children, right? So let's do it again recursively bottom up. So let's calculate the not of P and not of N. So not of P in this case is not 1. So that will be 0. So this will be your new not of P will point to this. And not of N will again be 1. So that will basically point to this. And then you want to take these two and create a new node. So you'll create a node which contains as the positive child this 0. So the solid edge will go to this. And as the negative child, this one. So the dotted edge will go to this, right? So this now is your new X bar. So let's maybe clean this up slightly. So this is your X bar. And you have a solid edge to 0 and a dotted edge to this, correct? So this is a situation. We're doing this example just so, yeah. This is a situation. And now we have, now remember that we are basically calculating B2 as your not of B3, right? So we have calculated X bar and that has been assigned to this pointer. That is B2 is basically pointing to this node, the X bar node, right? So now we want to do a plus, right? So again, how do we do a plus? So if you basically have a node which decides on the same variable, then doing a plus basically means you're going to or each one of the children of your node, right? So essentially what I'm saying is that if you have a node of this form, node, and you're deciding based on V, if V is true, you go to say P, and if V is false, you go to N, and you have another node. You're also deciding on the same variable V, and if it is true, you go to P tilde or P prime, and if it's false, you go to N prime, and you want to do a odd of these, this is basically the same as node V, P or P prime, N or N prime. Is this right? Yes or no?
Yeah.
Yeah. So essentially, when we did in this final operation, what we would want to do is, again, we would want to take these two nodes and do an OR, which is the same as taking the corresponding children of these two nodes and doing an OR. So the corresponding children in this case would come to the base case of a recursion, which is where we have either 0 plus 0, 0 plus 1, 1 plus 0, and so on, right? So these base cases we can basically just hard code in for when your children are just 0 and 1, right? So in our case, what we see is that what we would want to do is that we would want to create a new node where the two children would be 0 plus 0. So your negative edge, the negative edge basically is 0 and 1. So there is 0 plus 1. So then the child for your the negative child for your new node, let's call that say P plus P prime in this case, right? So P plus P prime would be 1, right? Similarly, the positive edge is 0 and 1. So again, N plus N prime is also 1. So now we create a new node, which basically is going to be our final function f, which sends both the positive and the negative edge to N plus N prime, right? So note here that here we only saw this, in this example, we only saw one sort of situation where your sharing happened, which was specifically in this B3, right? When we said B3 equals to X, we didn't actually have to construct a new X here and set that to B3, right? So we saved making one node in our example, correct? So is this particular example clear? Can I sort of erase this because I'll have to do these other examples as well? Is this clear?
Yeah.
Yeah. Okay. So yeah. So this is this simple example. So let's now look at maybe X plus 0. Maybe I should have looked at that before, but it's okay. So one thing that I'll basically not erase is these recursion expressions, because we can maybe formalize them and write those down as algorithms later on. Also, I shouldn't have erased that BDD there. Maybe I'll write that down again. BDD. Correct. So yeah. Okay. Let's add. Do it piecemeal. Right. So this is for the your not case, and is this recursion complete for the not case? Like, are these all the cases that you can have with one single node? That your node is either some positive, negative, and okay, there should be some variable here, and it should be on the same variable, right? So maybe I'll rewrite this. So you have your node VPN and node V not P not N. So for the not case, is this recursion complete? Does it deal with all the cases? And do you think that it is correct, or are there any mistakes? Is this complete? Yes or no?
Yeah.
Yeah, right. So this deals with all the cases. So we will see, actually, when we go into this example, we'll find the answer to this. But does this recursion deal with all the cases? So I'm not writing down the constant cases. So we have node whatever, comma. Okay, actually, maybe we'll think about that later on. So node whatever, comma 0 is plus 0 in this case, right? Plus 0 should be just node whatever. And similarly, we'll have node whatever plus 1 as being just 1, right? So we can add these two recursive cases and use that for this example here, right? So in this example, again, let's say that the algorithm takes the left branch first, and we create your X. That will be solid H2 1, dotted H2 0, right? And then the right branch will just be 0. So this is, say, your, again, say you're basically doing your final B is B1, B2 plus, and this is going to be your B1, and then B2 is going to be just 0. So B2 is going to point to just here. So B2. And then when you do plus, since we have defined this, and okay, when I'm saying this, I'm also in like assuming that the, you know, the 0 and the node can switch places and all of that. I'm not writing all of those cases down, but yeah. So since we have defined this, we can immediately say that B will also be just this, right? So is this fine? Does this make sense?
Yes.
Yeah, right. Okay. So now let's come to the third example, which is a bit more interesting. Yeah.
B should be on B1,
Right. Hello. So okay. No. B should. I'm sorry. I made a mistake. This is why I'm asking whether it's correct or not, because I do make, like, I mean, yeah. So in this case, because B1 and B2 plus is happening and B2 is 0, B will just be B1, right? Yeah. Is this correct now? Paramala?
Yeah.
Yeah. Right. So yeah. So the second example is also okay, I think. So now let's come to the third one. The third one is interesting, a little bit more interesting, because it actually has two variables in there, right? So okay, how am I doing in terms of time? Okay, let's see. All right. So in the third one, again, let's go to the left branch. So it again takes X, positive H2 1, dotted H2 0, and then say you have your Y, right? So in the right branch, it is. So let's again say that the first call was B1, B2 plus, and in our case, this is B1. So B1 is completely constructed now. Now we'll go to B2. B2 is not of something. So B is equal to this. B2 is equal to B3 and not, and B3 is some Y. So B3 in this case would be Y. So we don't have a Y here. So we will have to construct that as a new node, which we can't do much about, right? And now what we do is we want to take the not, right? So we want to do a not of this B3 here. So this is our B3. So as we saw before, the not, what that does is basically it will just take your children and not them. So in this case, this was your P, this was your N. So this will become your not P, and this will become your not N. And B2 will be this new node where the positive one points to not P. So like this, and the negative one points to this, right? So this is your B2 node. So let me write, okay, this is B2. So let me just erase the B3 node, which, let's imagine that there is some garbage collect. There are usually garbage collectors with BDD packages that will take care of and remove nodes that you're not using anymore. So yeah, let's see if I can surgically erase this. Yeah. Right. And this node decides based on Y, correct? So this is your B2 node. So B1 and B2 are done, and now we want to do a plus. So now we see that this recursion that we had written for plus is actually not complete, because there is another case. There is a case where your V and V prime, like these two V's, they may also be different, right? You're not deciding on the same variable on each one of your nodes. So what do we do in that case? What would make sense? What do you think the recursion should be? Anyone? Right. So essentially what you can sort of think of, or maybe imagine this as, so let's assume for now that Y is always above X, and let's rewrite this much more, a little bit better. So we have your Y here and your X here, and we have 1 and 0. So x is solid to this, dotted to this. Y is dotted to this and solid to this, right? And this is your B1 and this is your B2, right? Yeah. So now what would happen essentially is this, right? So you have your B1 and B2. If you want to sort of do an OR and say that y is greater than x, you can sort of imagine this situation as being that, okay, there is some ghost x node here, right? And then all the decisions from the x node are going to wherever that particular edge of your y node is going. So similarly, take the negative edge of the y and imagine that there is actually a y here, and all the edges from this new y node, both the solid and the dotted edges, are going to your the same thing as the original node was going to, right? So, okay, sorry, this will be an x. So then now that you have this, then you can sort of imagine your structure as being this, right? So you have a node on y and you have some positive and negative, and then you have some node based on, so then you have a node which decides on x, and then you have some other different positive and different negative, and we know that x is less than y, so x comes below y in our variable ordering. So then what we can do is essentially this, since we're not deciding on the same variable, this is equivalent to saying, so saying that, okay, we're going to add these two up is equivalent to saying that we are looking for a node that looks like this, right? Node P with the positive edge is P plus node of x, P prime, N prime, and then N plus this same node of x, sorry, not x prime, x, P prime, N prime, right? So, sorry, this should be N, just so that we don't get confused later on. Yeah. So is this correct? Is this as a recursive sort of formula correct? Is the node that we're looking for, will this node be a node that decides based on y to go to whatever y went to plus whatever the value x comes out to be, and whatever y, like if it is y is false, then it will go to whatever y went to plus whatever the value of x is. This is correct, right? Because if you yeah, right, because if you imagine the if then else structure of this one, this is basically saying that, okay, if y is true, so let's restrict y to true, then what you get here is p, and this doesn't reduce, so you get this expression. And if you restrict y to false, then what you get is n, and this doesn't reduce, so you get this expression, right? So this is correct.
I have a doubt in the diagram.
Yeah.
Okay, the solid line means and the variable is assigned 1, right?
I couldn't hear you. Can you come again?
Yeah. So in the diagram you have drawn here, right?
Yeah.
So the solid lines means the variable is assigned 1, right?
Yeah.
So from y we are going to when y is 1, we are kind of going to 0, right?
So when y is 1, we would want to go to, no, B2 was, if you remember, not y, right? B2 represents the formula not y.
Yeah, B2 was
Yeah, this is x plus not y. Yeah.
So
yeah,
this x plus y bar, this expression will go to 0 for only one assignment, right?
Yeah.
But if you look at the graph from y is,
this graph does not have the x plus y bar expression yet, right?
Oh, okay.
Because this graph just has the x and the y bar. There is no node for the x plus y bar yet, right?
Okay.
But
so
yeah,
what you have drawn is just an intuitive approach to deal with this, right?
Yeah, or you can think of it an intermediate steps. If I ignore maybe these nodes that I had drawn for intuition, and just have your
Okay.
yeah. So this is an intermediate step. So we have computed B1 and B2 right now, right? And now we want to compute B1 plus B2.
Okay. Now it's clear.
Yeah, and as I was saying, this recursion would be fine, because if you are basically have a situation where you want to add two nodes where one variable is above the other, let's call that variable y and the lower variable x in our case, then what you would want to do is basically create a new node that decides on the higher variable. And if the higher variable is true, then you go to whatever the OR of the positive edges node and the lower variable node is, and whatever the OR of the negative edges node and the lower variable node is, right? Because this, if you look at this expression, so maybe let's move this a little here, right? And yeah, so if you look at this expression, if you restrict y to 0 or y to 1, then you get this expression. Otherwise, if you restrict y to 0, you get this expression, correct? Because if you restrict y to 1, this expression reduces to this, but this doesn't reduce anywhere, because this, as we know, because of the variable ordering nature, this does not contain any y, so it remains the same. But if you restrict y to 0, this will reduce to whatever the value of n is, but this doesn't reduce because, again, it does not contain any y, correct? So the recursion would basically, in the case where you have y greater than x, be just this, right? So this is another recursive step that you would want. Now, so in our case, what we would want to do in that case is basically compute these sub expressions. So let's call these some. Let's call this some.
Can you once again
yeah.
explain why that node of y pm plus node of x p bar n bar does not capture all the cases?
This one?
Yeah, you just said.
Yeah. So it specifically does not capture the case where there is two different variables in the nodes. So if either on one of your node is just a 0 or 1, those is captured by.
Okay. Not that one. The bottom right side.
This one, right?
Yeah.
No. So this is the only case that is not captured by this one.
Okay.
I'm not. Yeah. So I'm saying that this, what we had working with for the like the OR operator, was up until this point incomplete, but this will complete. This is what I'm basically saying.
Okay.
The only case what we had missed here is basically when one of the variables are different, right? And that is basically being captured by this, right?
Okay.
Yeah. And is this case clear, the correctness of this part? Is that clear to everyone? Hello?
Yes.
Yeah. Okay. Yeah. So yeah. So again, to do this, we would want to compute these internal sub nodes. So let's call them B4, B5. So B4 again is P plus this one, right? So it's this one in our case was, as we remember, B1. So let's maybe rewrite this. So what we're wanting to calculate is this, right? So we want to calculate node of y, and P in our case was just 0. So we have 0 plus node x at P prime n prime in our case was B1. And then we have 1 plus B1, right? So again, now we come to, so now we see that recursively to calculate these, if we call these B4 and B5, we basically end up hitting this case, right? So B4, we know that will immediately become just B1. So this is B4. And B5 we know that immediately will become just this. So this is B5, right? So finally, if we call this is our final B, right? So our B will be some node here, which decides based on Y. So let me make sure that it is drawn in on the same level. This is our B. And if B is true, so the solid edge goes to B4, that is X. And if B is false, that is the dotted edge, goes to 0. Sorry, it goes to 1 directly, right? And again, we now see that this node B2, we are not really, we do not need the node B2 anymore, right? So the garbage collector is going to, I'm not going into too much details of how this garbage collection and all of that might work, but that this maybe you can, it's better to figure this out while you're implementing, maybe, because that is too much detail to, like, it's hard to talk about that in just on the blackboard, maybe, right? But if you have some questions and if you think that something should not work, then do stop me. Yeah.
Like here we like took the ordering as y, then
Yeah.
after that x, right?
Right.
So it could be also in the other way, right?
Sure. Yeah.
Like the definition is like we are giving the definition for the ordering, or is it based on our definition the ordering is set, or is it something else?
So basically the ordering is going to be set, well, let's not go into what the ordering is practically set based on, but basically the ordering is fixed at the beginning of your program. So essentially when you're writing a program, you would usually not have string variables names like x and y. You'd usually just name your variables as integers 0, 1, 2, and so on, right? So the ordering is just then that 0 is greater than 1 is greater than 2, and so on. So
so here we like define node y p n plus node x p prime n prime,
right.
as node y p plus node. So it could be also in the other way, right? Node x of p plus node of y p n.
Yeah. And then x is less than y, right?
Yes.
So but you know
x
that
will
plus,
be
yeah, but you know that plus is like commutative, so you can just rewrite that as this,
yeah.
right?
So I'm asking that this definition is like we are giving y more prior, like y is the
Yeah. In our definition, in if you want to treat this as a formal definition of your recursion, then yeah, y is whatever your larger variable is, and x is whatever your smaller variable is. Is that your question?
yes, yeah.
Yeah. Okay, yeah.
That's what.
So that is clear, right? Yeah. Yes. Yeah. So I think I do have some more formal things on the other slides, but yeah. Okay. So let's just clean this up a little and maybe write down these 3 cases together somewhere. So it's okay if I erase these, right? Yeah. Yes. No?
Yeah. Yes.
Yeah. Okay. Thanks. I just don't want to erase and then. Right. And so I'll erase these things. Right. And then, yeah. Right. So yeah, so these are your sort of cases for this recursion. Okay. So yeah, let's maybe draw a partition between these two. Okay, so there are 3 examples here, but I think I'm just going to take a little while to do one more example, which is this one. So x, y, so that is x and y plus x and y. So do I have time for this? Maybe I don't. Okay. So I'll just do this quickly. So again, so x and y, what will that look like? So you construct you have your 1s and 0s. You construct your x as this. Sorry. This is your x. Then you have, so let's again say that y is greater than x. So then you have y here. And this is your node. This is what the y is basically, right? And then when you take an AND, what will happen is basically you will again have to AND. So just as we did OR, everything in the AND is actually just the same. It's just that the cases where we have constants will be different, right? Is that clear to everyone? All of this goes through if you replace plus with AND, is except for these, which will just change according to the behavior and, right? Is this okay?
Yes, yes.
Yeah. So similarly over here, when we're doing this, what we'll end up doing is basically AND of x and 0, that is just 0. So this, whatever new node that we'll have for x and y. So let's call this the x and y node. This will be the 0, 1 will go to just 0. And of x and 1 is just x. So this will be your x and y. And again, let's delete this node because we don't need it right now. So we are right now only working on the left branch of this, right? So we're working on the left branch. And now we have done the x and y computation, right? So now this is the, I think this is the point that Paramila was asking there as well. So now when we actually want to calculate this same x and y for the right branch as well, notice what happens is that again you construct x. So then you again, okay, you will need to deconstruct this y node. But let's say that the garbage collector is smart enough to do it at the end, or let's ignore that little bit of the cost for now. But when you do this AND operation, note that you'll see that the node that you want to create has as its negative child 0 and as its positive child x, right? And you see that you already have a node here that has those properties. So you again, so let's call this one, if we call again B1 and B2, this is your B1. You would again set B2 to the same node here, because you won't recreate a node that you already have if it has the same children as you had. So whenever you're creating new nodes recursively in these cases, a good BDD implementation, or any actual like correct BDD implementation, in fact, doesn't, when you're creating a node, it won't create a new node if it checks that, okay, the node that I'm creating, that there is already a node with those specifications in BDD, right? It'll only return a pointer to that node. So in that sense, we don't ever have duplicate nodes while we're working with this, even though we have multiple functions and have pointers to multiple intermediate functions. Even though we have that, we never carry around duplicate nodes at all, if we can help it. So does this maybe put some perspective on your doubt as well, Paramila? Yeah. Hello, am I audible?
Yeah, you are audible.
Okay.
I think Paramila is not audible.
Okay. Yeah. Okay. So okay, I'll move on for now. Right. So now we have, I think this is the your recursion being written as more formally. So if you have the same variable, this is the same variable case, then x goes to T1 and T2, x goes to S1 and S2, and you have some operator that basically reduces to x goes to T1 operator S1 and T2 operator S2. And now if you have say you have this is your T is your lower node, T is a node on lower variable, lower than x1 var, then in this case T operator x goes to S1 S2 will basically become x goes to T operator S1 T operator S2. Similarly, you have the commuted one version of that, right?
So can you hear me now?
Yeah. I can.
Okay. Can you move to the previous slide? I have one.
Yeah, sure.
Now, for B2, we have written x dot y, right? Now, instead of writing it as x dot y, what if we have written as not x or not y? It will essentially be same as x dot y.
Right.
But it's not easy to see that they both of these terms are same, right?
Yeah, exactly. I mean, so if you're so as a general answer to your question, if your terms are very complicated functions that they come out to be the same, then you will end up creating a lot of intermediate nodes which you end up deleting later on. For instance, here also you had to recreate this y node technically and delete them again, right?
Yeah,
So
okay,
so
okay.
that can happen. But my point is that if at all there are nodes where you can, like, you say your intermediate functions in those cases also are a part of this existing graph, then they'll be shared, right? So exactly, as much as you're maintaining over here will always be shared, and you can somewhat control that with UDD as well, how much you keep and how much you discard and all of that.
Okay.
And of course, yeah, and of course, like, there are, depending upon how well you know what formula you're working with, there may be very smart ways of doing it. In this particular example, if you have x bar plus y bar whole bar, I think a COBDD implementation will actually not have to redo much calculation, like too much calculation at all in that case, and that you can maybe check for yourself, right?
Okay.
Yeah. So just in this case, but in general, of course, what you're saying can happen. Yeah. So yeah, this is just the apply. This is general apply function for any operator that you can like a pseudocode for this algorithm that we have described up until this point. You can go and read through this and see that what we had been doing is basically the same as this. I'm not going to sort of spend time on this right now over here. So yeah, so there are two more operations that we would want to work, like one we would want the BDD to have. And so those two operations are your restrict operations. So restrict is basically you want to basically take a particular variable and set that value to, say that particular variable's value to 0 or 1, right? So again, we can think of how we want to do this. So you basically, this, I think you can, of course, you can think of it as recursively working on BDDs, and you can write a recursive function for this and that will work. But it's actually easy to look at this as an iterative thing. So you go down to, so each variable corresponds to each level in your BDD, right? So you go down to the level which corresponds to your BDD. So let's look at this particular example here. So you go down to the level of x2, let's say. Then you're restricting x2 to 0. So you know that these edges should not exist, right? And you know that any incoming edges to any x2 node will always directly go through the dotted edge. So what you do is you delete all your x2 nodes and take all the incoming nodes and extend it according to the dotted edge. So essentially what you do is you have your x1 and you had a dotted edge going to this x2 node. That dotted edge now gets extended all the way to 1. And you had your x2 and you have a solid edge coming from the x2 to this x2 node, to the right x2 node, and the dotted edge from the right x2 node was going all the way to x3. So this new solid edge will now get extended all the way to this x3 node, and this x3 node remains the same. Sorry, this is a solid edge, same as it was before, right? So this is the restriction of your function. So notice that this edge got deleted, this edge got deleted, this node got deleted, this node got deleted, right? So yeah, this is how you can basically implement a restrict function for your BDDs. So yeah, another function that we will need a lot of time is existential quantification, right? So the reason why you want to use your BDDs essentially is that you want to represent your reachable sets. And so Sir has talked about the fixed point iteration of the for CTL model checking, right? Hello?
Yeah, he talked about
Yeah. So you basically, there you had to deal with these reachable sets of under various operations, right? So the place where you would end up using, or we would end up using BDD, is essentially to work with these reachable sets. So for us, this elimination of existential quantification, eliminating a variable by adding an existential quantification of that variable, is actually very useful. It will come up in like all your operators that you're going to do fixed point analysis over. You will have to basically do this for several variables, right? Because you basically would want to say that, okay, does there exist a next state under your transition relations as that such and such things happen, right? So so yeah, so existential operator application is kind of important to us, and the way you can do this is by taking taking your f, restricting the 0x to 0, restricting the x to 1, and then applying an OR over it, right? So this is one way you can do it, right? So this actually requires one apply call, like that is one recursive call using plus, and then two restrict calls. The restrict calls, we can imagine that they may be fast, but the apply call is actually recursive, right? And this can be like somewhat expensive for when we are working with large formulae. And what would often happen is that your existential quantification is usually over a state which involves multiple variables. So you may have a formula like exist x1 up until xn and then f. And then if you do this particular existential, like if you use this particular formula again and again, if you apply this n times to do this, you're basically traversing down the BDD and doing n recursive calls, right? So that might be somewhat expensive, and let's see that how we can mitigate the expense of that. We cannot completely eliminate it, but we can mitigate it in somehow. So one of the ways we can do this is when there are multiple variables to eliminate, we can eliminate them simultaneously. So this is number one, and let's look at how we may be able to do that. So the idea there is, okay, so we have some pseudocode here, but the explanation is basically just this, that you have your, say, your f and g, right? And you have your e as your set of variables. Then if your f or g is 1, or if either of your f and g is 0, then you return 0, right? So this is basically for the case where you're looking at f and g, right? So similarly, you can do a recursive elimination over f or g, right? So then you have basically you select, say, your x and y are your top variables of x, f and g, and then z is the topmost of both of these. So what you want to do is basically take the restrictions of f. So basically you're taking the negative children of f and g, and you're eliminating over them, and then you do the relative product of that. Or you're taking the positive children of that, you're eliminating over them, then you take the relative product of that. And then if z is in your existential, like if this particular variable that you have decided on at the topmost level is in your existence, then all you would want to do is take an OR of these, right? Otherwise, what you would want to do is take an AND of this, or take your usual if then else operator. So the idea behind this is that if you have some node and you have the children going here, let's say, then and you have a set of variables, and let's say that this node is decides on this variable z, right? So essentially, say you have two nodes that you would want to basically like that is basically the two children of your original BDD here. So you have your two nodes, and let's say that one of them is z and one of them is something else, right? Or okay, fine, whatever, it doesn't matter. So then you have your set of variables e. What you would want to do to eliminate them simultaneously is that you would want to go here, eliminate them simultaneously here and here. So that is, and then you want to take do this recursive procedure for that, and that gives you your R0. So maybe that points here. And similarly, you have your R1 that basically eliminates it simultaneously here and here, and that will point here. And then if your variable then that which you're deciding, if either of them, or if the topmost one of them, right, is in your E, then you would want to eliminate that variable. So you basically take the OR of those R0 and R1 that you've taken, right? Otherwise, what you would do is basically make your usual if then else structure. So is this clear? Yes.
Yes.
Okay. So essentially what you're doing here is you're having to do twice 2 recursive traversals, right? Because if we think of it like this, so you have your traversal here along your f where you've set z to 0. So you have your traversal along your right f and g with your particular restrictions in place, and then you have your traversal along your f and g with the other restrictions in place. And remember that you can sort of when you're doing these restrictions, you can you don't need to necessarily like you'd basically be able to share a lot of these nodes, especially if z is fairly high in your variable ordering, right? So this doesn't require much additional node construction, hopefully, unless there is like the last variable or something, then in which case you're in the worst case. So you have your 4 traversals here, and then you're based on whether this one particular variable is in E or not, you're going to OR those 2 children, or you're going to put in the if then structure. So this, the good thing about this is that even if you have like this is actually the complexity of this is in some sense independent of the number of variables your existential quantification is over, right? But the cost of this is of course that you'll have to sort of do multiple traversals and so on. So is the simultaneous elimination clear? Yes, no?
Yes, I think so.
Yeah, to everyone? Okay, so I'll move on.
Yeah, it's clear.
Okay. So yeah, now what we come to is the second way of mitigating this existential elimination cost, which is if the image is under a transition relation, there are some specific optimizations that we can do, which is a good thing to sort of think about. So we have 2 types of composition or 2 types of transition relations, right? One is synchronously composed and the other is asynchronously composed, right? So essentially the synchronous composition basically looks like this, where you have your individual systems transition relation being given by this, or let's say the individual systems transition functions fi, and then you have your ri, which basically sets the variables belonging to that particular synchronous systems to their corresponding newer values, and then r basically makes sure that all of these particular relations hold, right? So there's an and here. So, and in the asynchronous case, what you have is basically your function, again, your transition function is fi, and your variable is, so your ith variable for your ith system would be, your I variables would be given by fi of your total variables, but all the other variables will remain the same, right? And then you're ordering all of these expressions. So notice that this is potentially a much larger expression because it's an OR of some huge and inside there you have the FIs, whereas this is just some conjunction, right? So let's see what some specific optimizations we can do to basically sort of mitigate the cost of this for these 2 particular cases. So for the asynchronous case, what we have is basically what we want to do is basically this, right? Ex of h would basically want to find you want to ask whether there exists some v bar prime. So v bar prime means the conjunction of all vi primes, such that some h holds on it, right? And from this current variable, there is a transition relation from v to v prime, right? This won't be r. I think this will r. I think it will just be r, if I'm not mistaken. Yeah, right. So under this situation, what we would want to do is, this is basically some so remember in this case we have some disjunctive partitioning, right? And we know that this particular variable, like this v bar prime, this occurs in each one of them. So we'll have to basically work with the disjunctive partitioning in this r over here. What we'll have to do is basically split this existential over the disjunction, and we'll get existential in each one of these disjunctions, right? And then the question is, we cannot avoid this, but the question is how can we sort of calculate this in a nice fashion, right? So this is again is existential over this entire V bar, and then this is over, you have your H V bar, and then you have one particular Ri over here. And if we expand this Ri out, this is basically saying setting Vi prime to Fi of Vi bar, and then all of the other Vj primes are remaining the same, right? And the existential is over all the prime variables. So since all the other Vj primes are remaining the same, you can see that you can actually drop the existential quantification over all the prime variables and substitute the Vj's primes with Vj's in H, right? Because asking whether there is some Vj prime, so that where such that Vj is equal to Vj prime and H of that holds, is basically just asking whether is equivalent to dropping the existential quantification and substituting the Vj prime into this H, right? So this is equal to quantifying over just a single Vi prime and putting Vi's instead of or Vj's instead of the Vj prime here, and you retain this particular expression, right? So this is actually much smaller because you're existentially, or we are quantifying over potentially fewer variables, and then you can conjunct them using this. So this is for the asynchronous case. So for the synchronous case, what you can do is essentially try to find some order which basically tries to move subformulas out of the individual quantifiers, right? And how do we do that? So essentially imagine this particular example where you have your R0, R1, R2, and this is basically for a mod 3 counter, sorry, mod 8 counter, but yeah, basically 3-bit counter. And then usually if you want to like use in the existential case, you have your like the synchronous case, you have this sort of a conjunction that in our case looks like this, right? You have your H of V prime bar, and then you have R V prime V0 prime, V prime V1 prime, V prime V2 prime, and so on, right? So then we can basically choose a particular order in which we push these existentials in. So there's an existential over V0, V1, and V2. We flip the existentials and we basically push them in. So we say that, okay, we'll existentially quantify over this one. So we calculate this particular part of this formula. So this existential elimination will only have to work with this small formula. And this will eliminate this V0 bar and only introduce one new V1 bar, right? And similarly, this one will eliminate this one, and this will basically work over this smaller formula. And remember, we've already done the elimination here. So this is hopefully going to be some smaller formula. And similarly, this one will work over this smaller formula. So we can basically push these existential quantifications in using some smart ordering and basically split our work up so that we have to do existential quantification fewer number of times, or in this case on smaller formulas, right? So this is some specific optimizations that we can do, and this is the end of our slides. And
I just want, I'm back. Okay, I just wanted to add one thing. I think the order there, you will have to do some analysis of which functions depend on which variables, or actually which functions don't use a particular variable. I mean, in those R0, R1, R2. Okay, so you need to do that analysis ahead of time, so that then you could have an ordering. Of course, the most optimal ordering trying to find out is difficult, you know, but nonetheless, it is based on some analysis of those transition relations, component transition relations, and you have to find out what variables are not used, okay? And then figure out the order.
Right. Yeah. So in general,
all these things are discussed. I mean, they are in the book, okay, in the reference book, Clark, Croning, et al. So you can look it up there as well.
Yeah. So yeah, in this particular case, for example, this order works out, but in general, you may have to do some like some smart analysis of your transition relations to figure out an order. So yeah, so this is all I had in terms of slides. So I have some exercises sort of things you can look at over here, and this is a summary of what we have talked about. So yeah, I'm going to not go too much into this since we are already out of time. So So yeah, I couldn't go into the actual demo of the CUDD package.
Yeah. Okay. Now I think what we should do is, okay, let's, are there any questions? So then I
Yeah.
will tell what the. So by the way, I mean, I want to go back to the question that I guess Paramalai asked about how do you know that there is, you know, like if you have f or not f or something like that, where f is a function, some arbitrary Boolean function. How do you know that there is only
That one, I didn't explain that one.
okay, good. Because see, there is only one node. I mean, usually in an implementation. Now, yeah. So in an implementation, because every function has a unique node that you created, so you can, you know, the actual implementation will maintain tables, and there is a lookup operation also, which given a unique ID for a node, I mean, it can check if it is there or not. If it is there, it is there. If it is not, then that function is not there. Okay, so that's what it is. Okay, so I'm glad that it got answered. These exercises, I mean, are actually these, there is complement arc BDD as well. How do you implement these operations? I don't know if you actually explained them, Diganta, but if you did
I did not.
Have the time, that would be a good exercise. Okay, I think I'm thinking of giving it. We can give them some hints, and with a little bit of thinking, you can actually extend the apply operation to work for complemented R. So you know, I think I'm to make in the second assignment there will be some written part. Okay, and of course the programming part will be your you know, CTL model checking building, for which you will need to you know how to use the CUDD package. What you can do, Diganta, is upload all the installation instructions,
Right.
and its program manual and so on. What I'm thinking of, maybe we can give, you know, you can also upload some code of doing something simple. Okay, they can review that on their own, and we can also give them, you know, maybe not a graded exercise to build something, and they, you know, that way they can actually get. And I think that is the part that you will have to get started on. And this comment is meant for class. So either you will have to have another class in which you do, but what I'm saying is that we can do on a need basis. This is my proposal. Okay, so you will upload all the information that is needed for them, including a small piece of code to, you know, do something simple as to how they would use. And actually most of these functions are there as library functions on the CUDD package, all the necessary operations. And maybe so you could have a code as to how you will initialize the BDD table, and, you know, some of the things that you need to do. That you can put it in a code example, upload it. I'm suggesting that the class, you know, the people review that, and we'll also include a small exercise that they can do, so that will be a good warm up for them to get started, you know, working on. Or we can even make that as part of the written part of the assignment of the thing. So that's my plan. Yes, is there a question?
No, it would be better if Tikanta has a free time. Maybe he can record a video about some simple exercises, and he can post the video in the Moodle itself.
If he has to do that, then he might as well offer another tutorial.
Yeah, I mean,
It might not be long, just for 10 minutes, just to explain the basic syntax and the structures.
Yeah, what do you suggest? So that's my thing. I mean, if you guys don't mind, I mean, then you can as well have a, you know, half an hour session at your convenient time.
Yeah, I think
I'm
I think
convenient.
I'm up for that. Yeah.
I just don't want that to be part of the regular class. That's all I'm saying. If it's all agreeable for you to do that, then he can illustrate the code that he's going to do and also explain. I mean, describe the exercise so you can do it. What would be, yeah. And
Yeah,
I think, yes, yeah. Go ahead.
Yeah, that works for me too. I can at a test session, extra session for
Okay.
half an hour.
Okay.
How
So
about the others?
I can too. When would it be?
Now that is something the four of you will have to work it out amongst yourself. It can't be on the regular class sessions. Anything outside is fine.
Maybe
Yeah,
we
okay.
can.
We'll discuss it with Amin as well.
Well, if it's fresh in mind, if you want to do tomorrow evening,
let me just check. I'll stop the share for now. Is that fine with you?
shall I stop the live stream?
Yeah. I mean, I think it's okay, right?
Yeah, if there are no questions, I'll stop the live stream.
So tomorrow, I think I can. Yeah. So it's fine tomorrow evening. Yeah.
I have some deadlines approaching tomorrow and day after, so I'll follow it on video. Like if it's recorded, I'll follow it on video later.
So I mean, if you want to, so yeah, I will record and maybe upload this as well. But if you want to suggest some other time, that also works.
Wednesday evening then? I mean, when is your deadline?
So I have 2 assignments and I have and a
Okay, the whole week. Okay, then
Yeah.
so that'll be the whole week. It can't be this week, right? So no, I don't want to wait till next week, but that'll be a little bit too.
No, I think Thursday evening is fine. It's due Wednesday. Like,
Oh, okay. So let's Thursday evening should be fine now. Diganta?
Yeah, Thursday evening is fine.
Okay, thank you. Yeah.
sorry, I forgot. There's another class on Thursday evening, 5 o'clock. Is there any other window possible?
So if Thursday is fine, I can also do Thursday like post lunch.
Yeah, Thursday
Yeah.
morning we have a meeting, correct, Diganta? So it has to
Yeah. It has to be post lunch. So post lunch
Post-lunch.
Thursday, I'm free. Yeah.
Is 2 p.m. work? Does it work or 3 p.m.?
3 p.m. works. Yeah. Does 3 p.m. work for everyone?
Thursday we have a LOPT class at 3:30.
Oh, okay. So I can do something. I'll try to do it from 2 to 3:30 on Thursday or 3:15.
Yeah, I think I'm the only one who is taking those classes. So I cannot attend and the other two can attend.
I mean, yeah,
I'm
but
the only one who has the deadlines. So
yeah, but we do have just 3 people as well. So
Yeah, I mean, it's a small class. That's why
yeah,
I'm willing to be, flexible to a certain point.
So maybe it's best you can post just resources. We can follow it up, I guess.
So I can do Thursday 2 to 3:30 is fine. I can make that work if it is okay with everyone.
No, but if Ratnakar can't attend that anyway, so then you might as well do it tomorrow evening itself.
Oh, okay. So Ratnakar, is Thursday 2 to 3:30 also not okay for you?
for me, Thursday I have only one class and that's from 5 to 6:15. But
So
I
2 to
think the
3:30.
others have a class in the afternoon.
No, but
Is that
2 to 3:30, no one said had a clash, no?
Yeah, I think Thursday 2 to 3:30. Amin has a class, I guess, PLC, but I'm not sure.
Oh, because Amin is not here today, is it?
He was
I think
here.
it
He just left at the last time.
Oh, I see.
think
Okay, then I do understand.